Okay, so good morning, everyone. It is a pleasure to have Asaf Miron here with us to give the seminar today. Asaf did his undergrad studies in the Technion and is now doing his PhD with David Mukamel. And he is going to tell us about whatever is written on the screen. So I just want to remind you that giving a talk through Zoom is really, really hard because you can't see the people. And so you don't know if you're getting through. So please, please ask as many questions as you call. And yes, of course, congratulations to Yossi Klafter for the Israeli prize. So with this, please, Asaf, please start.
Okay, so thanks, Yael, for the invitation. The title of this talk is Universality and the Onset of Super-Diffusion and Anomalous Transport in Lévy walks. Now, please don't worry if some of the expressions in the titles don't sound familiar to you yet, like super-diffusion, anomalous transport, or Lévy walks, because they'll all be explained in an intuitive manner very soon. Now, that said, I'm excited to share recent results that show universality in the onset of super-diffusion, by which I mean that there are universal rules that govern how super-diffusive systems approach their long-time and asymptotic behavior. Now, this claim is based on results that were derived for the Lévy walk model, which is a popular model for super-diffusion, and they're supported by a recent study of 1D anomalous transport. Now, what these results suggest is that Lévy walks could be a very valuable tool for studying super-diffusion beyond the asymptotic limit, which is the only relevant regime in most experiments. And the talk is mostly based on the first two references, and I'll only briefly mention the third one. So here's an overview of the talk. We'll start with an introduction on diffusion, super-diffusion, and the Lévy walk model. We'll then discuss the onset of super-diffusion in Lévy walks under equilibrium settings. And finally, we'll see evidence that suggests that Lévy walks describe super-diffusion beyond this asymptotic limit by studying 1D anomalous transport in non-equilibrium settings. So we all know that diffusion describes an immensely broad range of phenomena. So for example, the motion of a grain of pollen through a glass of water, or heat propagating through a metal bar, or even foraging predators in prey-abundant environments, right? So what makes diffusion so widespread? Well, in many complex systems, microscopic dynamics kind of give rise to numerous seemingly independent and random steps, which in turn evoke the center limit theorem and diffusion. And just to get into this business, let's briefly recall how center limit theorem gives diffusion. So consider a random walk that's composed of many independent random steps. We'll denote them by yi, and they have mean 0 and finite variance sigma square. Then the position after n steps, which we denote by xn, is itself a random variable. And by center limit theorem, it has a normal distribution with variance n sigma square, where n is just the number of steps, and sigma square is the variance of each one of the steps. Now, the Galton board is a nice illustration of just how seemingly random trajectories of many beads, in this case, give rise to Gaussian statistics, Gaussian distribution, which is nice if you've never seen. So in the limit of continuous time, we can replace the number of steps n by t. And if we also replace sigma squared by 2d, we get a familiar propagator of the diffusion equation, p of x and t, that we've probably all seen irrespective of our background. Now, the hallmark of diffusion is a mean square displacement that goes linearly with time. And we'll adopt this as our working definition of diffusion. However, other dramatically different types of diffusion are also observed. So in these cases, the mean square displacement scales as t to the power 2 over beta, not as t to the power 1. But as a special case, we see that for beta equals 2, we recover regular diffusion, normal diffusion. And for example, for beta equals 1, we get something that's called ballistic diffusion. And by that, we simply mean that the mean square displacement grows like t squared rather than t. So it goes faster with time. And in this talk, we'll be concerned exclusively with super diffusion. Okay, so super diffusion is the regime between 1 and 2. Now, okay, so you see this definition, and you may ask, how different is super diffusion from normal diffusion, right? I mean, the second moment scales a little differently in time, but how big of a difference could that make? Well, we can get some intuition from a very helpful illustration that was taken from a canonical review on super diffusion, anomalous transport, and Lévy works by Ralph Metzler and Joseph Klafter, who I think I saw his name among the participants. And it shows 7,000 steps of a random walk with, on the left, you see just simple diffusion, so beta equals 2. And on the right, you see a different kind of random walk in which beta is 3/2 and it's super diffusive. The mean square displacement goes like t to the power of 4/3, which is larger than 1. Now, what you kind of see already, okay, without even getting into many details, is that super diffusion kind of looks a lot like diffusion, only that there are these ballistic kind of lines or excursions that kind of take the walk to different places. Now, if you were to contract them, you just take these lines and shrink them down to a point, and you get something that looks a lot like diffusion. And I think that's a very good intuitive picture of what super diffusion means. It kind of looks like diffusion with these long ballistic excursions. And having an understanding of what super diffusion looks like intuitively, let's have a few physical examples of super diffusion to look at. So, for example, swarming bacteria exhibit super diffusion, apparently, with beta that's about 1.27. Now, in this figure, you see in B, you see a bacterial colony. It's called B subtilis, and it's a bacterial swarming colony. In figure A, you see a magnified view around the region where this arrow is pointing. And in C, the lights are switched off, and they reveal a few fluorescently marked bacteria. In D and E, we then look at the individual bacteria trajectories at different magnifications. So in D, it's the zoomed in kind of part of the figure, and it looks sort of like diffusion, right? I mean, there are these excursions, lots of random excursions, but when you zoom out, you see that these kind of diffusive bouts are connected by these long excursions that kind of reveal that it's super diffusion rather than just regular diffusion. Another example is the spreading of energy fluctuations in some interacting 1D systems, which is also super diffusive. It's super diffusive with universal values of the exponent beta. So you can't have any beta you like in these systems. It only comes in very particular values. So 3/2, 5/3 are the most common universality classes, universal values. And I'm in advance, I'm saying I'm not going to go much into detail about universality classes in these sort of systems, even though they'll be important, because that's the topic of a whole other talk. It's a little involved. But I do want to say that this sort of behavior, this super diffusive spreading of energy fluctuations happens in systems, one-dimensional systems that conserve both the energy and the momentum. So you can think of just Hamiltonian dynamics that don't have a global potential U of X. Okay, so just interactions. Now, I'm going to ask you to please remember this example because we'll get back to it again and again throughout the talk. And I want to talk about the system that they were studying here. This system is very simple. It's hardcore particles, or by this I mean particles that can't go through one another in 1D. And they have alternating masses. So you see here there's lowercase m and capital M, and they are arranged like this from the get-go, from the beginning, when you release the system. And the role of the alternating masses here is to break integrability. So if the masses were all the same, all of these particles had the same mass, then upon collision, they would just replace their velocity. If they conserve momentum and energy, the only option is to replace the velocity, and it would be as though they are going through one another. So whatever initial distribution of velocities you start with, if the masses are the same, that's what you get forever, and the system doesn't thermalize. That's not a very interesting model to study. But when the masses are different from one another, then breaks integrability, the system thermalizes. And this sort of system, this kind of gas system, belongs to the beta equals 5/3 universality class. And that's the main one that we'll be thinking about in this talk. Now, this figure here on the right shows a collapse of the energy-energy correlator of this system, of this macroscopic system, for different times. And it reveals that it has a scaling form. Okay, so you see that this central region here collapses. These are all different times. Different colors here represent different times. And there is a very nice collapse that you see here, and you also see it throughout the tails, except the ballistic part of the tails that in the long time limit won't be interesting anyway, and we won't think about them here because they're not the interesting part of this behavior. And the inset shows, so first of all, you see that the energy correlator it has a scaling form. So it scales this way, and this scaling form implies that the mean square displacement grows like t to the power 2 over beta, and that's the reason I'm calling it super diffusive. Now, in the inset, what you see is the energy correlator at a particular time, and you see that in the solid black curve. And superimposed on top of it, you see a Lévy walk, which is the dotted red curve. And Lévy walks, I haven't introduced them yet, but they are a model for super diffusion. So what I'm trying to show here is that this system is super diffusive. So you see it both by the collapse, and you see it by the fact that it's described by a super diffusive model. And there are many, many additional examples of real physical systems that exhibit super diffusion that we just don't have time to list, but trust me, they are abundant. Now,
Asaf?
Yeah.
Is it important that the system is 1D?
Yes, it's crucial actually. Okay, if we really want to go into the details, then this physics is described by a recent theory that was introduced by Herbert Spohn quite recently, that's called nonlinear fluctuating hydrodynamics. And it shows that kind of in one dimension, the minimal hydrodynamic equations you can write give you this sort of scaling form they give you this sort of scaling form with different universality classes. And the fact that it's 1D is very important because you have to have basically 3 conserved hydrodynamic fields, which in one-dimensional systems are just the mass or the particle density, the momentum density, and the energy density. Now, in higher dimension, you have a momentum density that's conserved. Okay, now these are 3 hydrodynamic fields because they correspond to microscopically conserved quantities. Now, if you conserve momentum along different axes, additional axes, then you have more conserved fields. Now you have the momentum along each axis, and that gives a very different kind of behavior. But again, that's a topic of at least one extra talk, so there's no chance I can talk about that too.
Okay, thanks.
Sure. So we now talk briefly about the corresponding limit theorem for superdiffusion. So we showed before that the central limit theorem kind of implies diffusion, and in the same way, generalized limit theorem will imply superdiffusion. And we'll see this now. This is a very minimal definition of the generalized limit theorem, and it's tailored precisely to our needs. And so I hope there are no mathematicians that are offended by that are sitting here and are offended by this introduction because it's imprecise. But it will tell us what we need to know. So we now consider a random walk where the steps yi are drawn from a heavy tailed distribution, P of y, which we'll take to be symmetric, just for simplicity. And for beta between 1 and 2, what's different here is that the variance will be infinite. So that means that you have unbounded fluctuations, essentially. So by the generalized limit theorem, after n steps, the distribution of the position is not a normal distribution, but rather it's a stable distribution. And what's a stable distribution? A stable distribution is a distribution that satisfies the following. If you take a linear combination of random variables, and that linear combination has the same distribution as the random variables themselves, the distribution is called stable. That's the definition of a stable distribution. So you see that this is kind of a generalization of the normal distribution. Like if I take normal random variables and I take a linear combination of them, I end up with a normal distribution too. But this extends this to distributions in which the variance can blow up. So the stable distribution also implies a scaling form. In this case, it's P of X, and there should be an N there, a capital N too. And it implies a mean square displacement that goes super diffusively, just like we saw before, N to the power 2 over beta. Now, there's a problem interpreting this. Okay, there is a problem interpreting this as a physical model of super diffusion. And the problem lies in the fact that you can have instantaneous infinite steps by this kind of naive adaptation of the model. So, you know, I'm saying this because in the central limit theorem, we kind of said, okay, so diffusion, that's like a physical model of a system. We can, you know, think of that as a model. But here it's different because, you know, the infinite steps are possible and they break locality. So they can connect very distant points instantaneously. And that's kind of, locality is a nice feature we'd like to have all our physical systems to have. So question to ask is, how can we resolve this discrepancy? Because we want to describe super diffusion somehow. Yes.
In the physical system that you've just described in the preceding slide, does the distribution indeed obey a power law with a heavy tail?
Okay, so we're talking about two different things. So this is physics, and what I talked about is kind of a mathematical, you know, theorem that tells you that if you take random variables, you put them together, you get some. They belong to some distribution.
Exactly, that's the question. What is the correspondence?
Right. And okay, so the answer is coming in the next slide. If it doesn't satisfy you, then ask me again, please. Okay. So we were here, and we just, okay, that's actually very timely. How can we resolve this discrepancy, right? So let's consider a different interpretation of the generalized limit theorem. So if we consider now strongly dependent random variables, yi, they take values plus and minus 1. Okay, so they have finite moments. Then now this strong dependence will make it so that our random position after a large number of steps will be just this series. And I've just, for example, what we'll do is we'll break the series into parts or into steps that have the same sign. Now, because they are strongly dependent, then you'd expect that if, for example, in your first step, you draw +1, then this affects the probability of drawing +1 again. And it would make it more likely that you'll go again in the same direction. Now, if the number of these steps okay, wait, so before I do that, so here is just one sort of realization of this. So in the first bucket, and I've also illustrated this here on the right, so you see this axis is the position of, say, a random walker that started initially here, and this axis is time. So you see maybe the first two steps were +1. So we go 2 steps to the right, and then the next 4 steps would be to the left, and so on and so forth. But then you could have a situation, if you appropriately choose the dependence of the steps, where you have just an unlimited number of steps, or a number of steps that scales with n along the same direction. And the generalized limit theorem, in this case, would describe the distribution of the number of summons in each one of these brackets. And now this is a very nice interpretation, I think, of the generalized limit theorem, where superdiffusion actually comes from correlations between the steps, which are much more satisfying than having these infinite unphysical steps that are instantaneous, and it leaves locality intact. So with this, I'll now tell you about the Lévy work, which is basically a statistical mechanics model of the generalized, of this interpretation of the generalized limit theorem. And we'll see how this works. And one thing that I didn't mention, and I would like to, is that in this picture, you can think of each step taking a dt to complete. And so these distributions correspond to times. How much time do you persist along one direction? And this is a good grounds on which to present the Lévy work model. So we do it in 1D. And we describe it according to its dynamics. So the dynamics, it describes the dynamics of walkers whose evolution consists of many walks of duration tau with a finite velocity, which is constant. And we'll see how it works. So it's very simple. You first draw uniformly a random direction, sigma, which in 1D is just plus or minus 1. And then you draw a random walk time tau from a distribution phi of tau, which I will tell you more about very, very soon. And then after you do that, you walk with that velocity, sigma v, where v is fixed, for example, 1 throughout the walk. It will always be 1. And you do that for duration tau until you reach some position, and then you simply repeat this. So again, you draw a direction and the time, and you walk, and that's it. And you repeat this process many times, and that's the model. That's the Lévy walk model. Now, to get super diffusion, you want the distribution, the walk time distribution, phi of tau, to be a power law distribution. And in particular, this is a particularly convenient distribution to take. So let's take phi of tau that has the following form. This is just a normalization constant that we won't worry about. We don't have to worry about, but these two are the important features. So this is a step function that imposes a cutoff at small times. So at tau equals 0, for example, the distribution is equal to 0. Otherwise, it will just not be normalizable. We could not normalize the distribution. And most importantly, this distribution has what we call heavy tails. So since beta is between 1 and 2, the mean of the distribution, the mean walk time, is finite. And that kind of implies or tells us that there should be something that looks like a random walk behavior, right? We'll draw some time, the mean time, and this is most of what we'll be doing, and we'll be making these random steps. However, the infinite second moment of the distribution, which again, it's very simple to see. You just multiply phi of tau by tau squared, and you integrate, and you just see that since beta is between 1 and 2, the second moment just has to diverge. Now, since the fluctuations are unbounded, you can kind of guess that the Lévy walk will be dominated by a few very long walks. So most of the time you have just finite walks, but then every once in a while, since fluctuations are unbounded, you could go a very long time in the same direction. And an important thing to notice here, again, is that phi completely defines the model. So the only input into the model actually is this phi. Now, the interesting observable in these kinds of models usually is the probability of finding the walker inside some interval x to x plus dx at time t. That's usually the quantity people are interested in for obvious reasons. And what you can do is you can write a self-consistent equation for this quantity. So it's this integral equation written here. It's very easy to interpret. So I'll do that very briefly, and this illustration helps a lot. So suppose, and to think about this, it's most convenient to assume that at time 0, you had not 1, Lévy walker. You had many Lévy walkers that were initially at the origin, and you look at a different time t, and you ask what contributes to this density at position x. Then there are two contributions, one coming from the original distribution. So particles or Lévy walkers that were initially here, and the first walk time that they drew is big enough to take them to x. So with probability 1/2, they would go to the right in this case, and psi of t is the probability of drawing a walk time that is greater than t. Okay, it's just the integral of psi of tau from t to infinity. So that's this contribution. And then these two contributions are just the probability of being, say, if the Lévy walker already changed direction at some point in time, then now the distribution is kind of smeared or spread out, and the densities at these respective points, x minus v tau and x plus v tau, can also lead to contributions to x. And so you have, we'll just look at one of them, say this one. So you have the probability or the density at this point at time t minus tau, and then you want to draw a time that exactly takes you to x. And you want to have another factor 1/2 here because you need to go to the right rather than to the left. And the same happens on the other side. So this is a nice, I think, self-consistent equation for p of x and t. Again, what I'm currently saying are well-known results. And this is a good description of, this describes the Lévy walk model. Now, the asymptotic solution of this model is known. So the model, again, is on 1D, an infinite line. And the asymptotic solution here, I mean the solution as t goes to infinity. Behavior is c as time goes to infinity. So in Fourier space, you can write down, I denote Fourier quantities by this hat, and 0 here tells us that it's an asymptotic quantity. Okay, and so it has basically this form, which is kind of, it looks like a Gaussian. If beta were 2, this would just be the Fourier transform of a Gaussian. But beta is not 2, it's between 1 and 2, and so it's super diffusive, and it has the mean square displacement that we go to expect a super diffusive phenomenon, right? Now, the problem is that even if you assume that there are only diffusive corrections to this behavior, say, let's choose beta is 3/2, which is right down the middle between 1 and 2. And you say, I want to observe super diffusion, but I have to beat diffusion. Suppose diffusion is the only correction. Then this ratio, I'd want it to be much larger than 1 in order to say I definitely have super diffusion. But you see that you need extremely long times. You need times that are much, much greater than 10 to the power 3 in order to distinguish very precisely between the leading asymptotic behavior and, say, a diffusive correction. But who even said that diffusion is the only relevant correction, right? I mean, there could be even more dominant corrections. And that's a serious problem considering that experiments are inherently limited to finite labs and to finite time. Now, this means that it's fairly difficult to reliably and to convincingly measure beta and model real super diffusive systems with Lévy walks. Now, in light of these difficulties, one would like a robust observable that could reveal beta before the system even reaches this asymptotic limit, right? And I'd like to present the main results of a recent letter that deals exactly with this issue. And these are the main results. So I wrote here the asymptotic solution from before so that we have it in mind. The propagator of the Lévy walk exhibits 2 distinct behaviors that are separated by a continuous transition at beta equals 3/2. So above 3/2, the correction is just simple diffusion. Any value of beta larger than 3/2 just gives you simple diffusion as the approach to the asymptotic behavior. But below 3/2, the approach is super diffusive. and it changes with the value of beta. Now, this transition can also be seen in the truncated mean square displacement, which is the mean square displacement limited to some time scale that we choose to be this. It's not very important that it has to be, it doesn't have to be that. It could be any finite time scale, just to make sure the mean square displacement doesn't diverge. So if you just integrate this over R, then this quantity diverges. And this tells you how it would diverge with time. And the reason I'm writing this down, I mean, okay, if I write down the distribution, then you don't need me to tell you what the second moment is, but it's much easier to measure in an experiment, say, the mean square displacement than the whole distribution. And that's why it's relevant. And what's nice here is that the transition and the scaling of the approach to the asymptotic form, they're independent of the short time behavior, say the short time behavior of phi. They only depend on the heavy tail, and they are just universal.
Long time.
Yeah, they're independent of the short time, and they depend only on the heavy tail of the distribution, and that makes them universal. Now, I'll just show you a few figures that illustrate these results. So here you see the log of P of X of P of K and T, so in Fourier space. And according to what we wrote before, this should just be the log of the asymptotic behavior and these corrections. And here I show stars denote the just numerical solution, numerical simulation of the model. So just the dynamics I showed you before, you run them. The dots show the numerical solution of the equation. So you can numerically solve the integral equation for Lévy walks, and the solution is denoted by these dots. And you see that, as you expect, they lie exactly on top of one another. Now, the thick curve shows you the asymptotic plus the correction, and the dash shows you just the asymptotic behavior. So you see here for a fairly large time that the correction, the leading correction, does a much better job of describing the behavior at a larger k, which is smaller length scale, than just the asymptotic behavior. And this is for beta equals 4/3, which is less than 3/2. And you can see that this goes on for quite a while. I mean, it does a much better job of describing this behavior beyond the asymptotic behavior, and the same can be shown for beta that's larger than 3/2. So here I take 5/3, which you know, I would hint that beta 5/3 would be important again throughout the talk. Now, so you know, you might not be convinced that the corrections are exactly what I said. I mean, there are still you know, subtleties there. So here I just plot the log of the simulated or the numerical solution of P, and I divide this by the asymptotic solution, and I plot these just as a function of the variables I expect to find. And so this should be, so a good matching with theory is just a linear collapse, and this is what you see for both cases. It works. So the corrections are really described by this behavior, and this is over several decades of this scale variable. Now, the truncated mean square displacement also has this behavior. So again, asymptotically, you just get what you expect. Asymptotic mean square displacement is super-diffusive. And then for beta larger than 3/2, it goes like T, so it's like diffusion. For beta less than 3/2, it's super-diffusive. So you see that here, dots show just the numerical simulation of the model. The asymptotic prediction for the mean square displacement is shown in this dashed orange curve, and the solid curve shows you asymptotic plus the correction. And you can see here in the inset, just this quantity divided by T to the power 2/beta. So it should, the asymptotic prediction is just this line, this flat line. And you see that the simulation is this these blue dots, and taking into account the correction shows that you get the correct scaling with time. So the mean square displacement also has these features, and above 3/2, you get the same behavior. So in our context, anomalous transport is just a manifestation of superdiffusion in non-equilibrium settings. And we've seen that the onset of superdiffusion in Lévy walks is universal, but it's possible that Lévy walks only describe asymptotic behavior of superdiffusive systems. So it could possibly not describe anything beyond the asymptotic behavior, right? It's a model, who knows? Now, an important question is, do Lévy walks really describe superdiffusion beyond the asymptotic limit? And so, as we said, this happens, and results of 1D anomalous transport study, a recent study, suggests that the answer is yes. Lévy walks do model superdiffusion beyond the asymptotic limit, which is great because anomalous transport is very hard to observe both in experiments and simulations because it requires huge systems in order to observe neatly. So if that is so, then we can use Lévy walks to study anomalous transport in finite systems, and finite systems are the equivalent of finite times, and we'll see this shortly. So before we talk about anomalous transport, let's talk about just normal transport. And yeah.
Sorry. Yeah. So before you move on to a new topic, just a question on the previous one. So you said, yeah. So you showed this this correction. It's very nice. I just wonder because you mentioned this topic. Your motivation was a better estimate of beta from the mean square displacement.
Right.
So can you please explain if I have this correction, how can I provide a better estimate of beta?
Sure.
Did you devise a systematic way to do this?
Sure. So I mean, okay. So what people usually would have to do is, right, they would just fit. They would do a least minimal square fits to the data, to some power law, and they'll see how good it is. Now this gives you another kind of bound. So you just have to test two kinds of behaviors essentially. You have to test, you leave this as a free parameter and this as a free parameter, and you see whether or not, and it's better obviously as a free parameter, and you see if this fit works, or if this fit works. And here you're imposing the power of beta. So just a second. So, it reduces the free parameters that you'd have, right? Otherwise, you just have, another free parameter in the power here, if you had no idea what to expect. So, yeah, I think
sorry, I don't understand. I mean, in the beginning, we only have one parameter. We just have for the mean square displacement, just beta. And now you're saying just don't do beta, just do a 3-parameter fit. And do 2 fits, and then out of that you can find which is beta, which is better.
So
with more parameters, I can always fit better.
That's for
true.
Sure. That's true. But okay, so the thing is that naively fitting only the asymptotic behavior could either work very well or very poorly. And the problem is that you have no control over which of these outcomes you get, because you don't know if you're in the asymptotic regime. If you're not in the asymptotic regime, you can very well find, you can just do naively this fit and get some value of beta, and it would be incorrect. It will be somewhere between, it will be some mess related to the asymptotic behavior and its correction. You would not be able to separate the two. But suppose that, you want to study, you want to pinpoint what beta is. And to do that, you have to account for the correction. There's no other way around it, right?
Okay, maybe I can ask it as maybe an experimentalist from a different perspective. You said before that you need to go to like I don't know, 3 orders of magnitude in time in order to get an approximately good fit to beta on a usual way. How much less how shorter does the trajectories needs to be if we use your approach?
Well, okay, so first of all, I said that you need to take much more than 10 to the power 3. 10 to the power 3 would make them.
That's good. That's even better. Okay, so how much shorter the trajectories can be and still get beta?
So that's a good question, and it would depend on exactly what you're trying to measure, right? Because that's the same question as asking how long do I have to wait to be in the asymptotic regime, and obviously that varies by realization, by one application to another. However, you do have a much better chance of describing the behavior this way if you know what the corrections are, right? I mean, that's a universal truth.
I guess, Asaf, I buy into what you're saying. I guess what we're missing is an example where we see you try to estimate only with the asymptotics, and it's hard, and you need so and so time steps to converge to the right result, and then you do it with the correction, even in one example or two examples.
Oh, I mean, this is the example
where you see that you can capture beta with less data.
Okay, so I think that what I show is almost what you're asking. I mean, I'm not trying to deduce beta. I mean, I already know the answer because that's how Lévy work is constructed. But I mean, you can see, I mean, without a doubt that it's so much better. It's far better.
So if I were to use this idea, I would fit my data to the asymptotic thing and extract a beta, which probably is not the right beta, but this is my first, the protocol. So I first extract a beta, and then I divide. So if you go back to the mean square displacement slide.
Okay.
This one, exactly. So now I have assumed that I have the asymptotic, I have extracted some sort of beta, and now I divide by, like what you did in the inset.
Yeah.
So the asymptotic, if everything behaves like the asymptotic, I should get a straight line.
Right.
But if I have a correction, I would see it in the data that doesn't lie on this straight line.
Exactly.
So this would be a protocol to
I mean, you could do that. You could do that. You could also just, very, naively take this data and fit it to this form or to that form. And one of them is going to work and the other is going to work not as well.
So as an experimentalist speaking, when you show the plot where you have the simulation and the two fits, taking account to experimental error, there's no way I'm going to be able to say which one is better.
I see. So again, I would guess that you'd have to, this is a theory done in my room, and adapting it to experiments and real life is the goal. One would have to think about what would be the best way to implement this, definitely. But nevertheless, I do believe that it gives a very serious advantage, and you see this here. I mean, again, errors, fine, but I mean, this goes on for a while still, and you see these differences become significant. So hopefully, this is something that could be observed in experiments as well. That's what I hope.
So one thing that I would consider doing is add in the simulation noise and see how sensitive you are to this.
Well, there is noise that's intrinsic to this behavior, right? This is a stochastic model. There could be, there are things to discuss here, definitely, if one wants to observe this.
For example, how many trajectories are you averaging over?
Exactly what I was saying. I mean, if you'll take only a few tens or hundreds of trajectories, the noise level will be much amplified.
That's true. Here, I think this data is for roughly 5,000 realizations. I see you laughing. It's muted, but I see you laughing.
It's reasonable.
It's reasonable. Okay. I mean, again, these are corrections, right? This is not the leading behavior. But nevertheless, if you're into finally determining this beta, then noise is something you have to take into account, right? I mean, that's enemy number one, I guess, for experimentalists. this problem. And if you want to measure to high precision this beta, which, you know, in anomalous transport in 1D, there are universality classes. People know that because this comes from theory rather than experiments. So people, you know, they already have a clean kind of idea of what's happening even before they measure. Maybe nature also follows universal betas for, you know, others, and maybe bacteria have universal behavior. Who knows, right? I mean, if you want to know, if you want to check these things, then you need to be able to determine beta to high precision. That's what you have to do. And so, yeah.
Can I ask a question about a feature on the previous slide? Yes, exactly in this one. So I see on the left, the real behavior is below the asymptotic one for large K, and then on the right it flips.
Right.
Yet the equation you have on top, we don't see a sign change.
Because I didn't tell you. Because I didn't tell you what D1 and D2 are.
What am I missing? D1 and D2. Okay, this is
one
where
of them is
the
negative.
sign change is buried.
Yeah, one of them is negative.
Okay, okay, I see. So okay, but there is a flip. There is a flip here that is buried in the. Okay, okay.
Right. No, that's a very good comment. Yes, I mean, this is actually kind of a signature of this transition. At the transition, the sign of the correction flips.
Okay, it was just not apparent from the equation, but okay.
Right.
Good. Thank you.
It's because yes, I didn't. For technical reasons, it was more convenient to write it this way, even though D1 and D2 have opposite signs. That's true.
Thank you.
Sure. Okay, so moving on, we want to see now whether or not Lévy walks can describe anomalous transport beyond the asymptotic limit. So we showed that Lévy walks has this universal behavior, have the approach, and we want to know whether or not it happens in other real super-diffusive systems. So we were here, and what I was saying that when the anomalous transport says the answer suggests that the answer would be yes, and we'll now see this. And let me just first say or remind ourselves what normal transport is. So this will be very brief. Suppose you want to study energy transport in a many-body interacting Hamiltonian system, just a Hamiltonian system that conserves energy, say. Then the usual assumption is that, okay, so first of all, if energy is conserved, then you have the conservation equation describing the energy. Now, our usual assumption is that if you have complicated interactions, they manifest macroscopically as just diffusion. And this accounts for this second equation. Now, if you want to find the stationary non-equilibrium behavior that comes with this, then you have this, now J is the stationary current, which in one dimension has to be constant, otherwise you have current flowing into a point and everything will blow up. So the stationary current just has, it behaves like this, where T is the temperature profile, and it's very simply related to the energy profile, right? It's just a partial derivative and heat capacity away from the other. Now, if you study this behavior on a finite interval L with baths that maintain a temperature difference, then it's very easy to show. You just integrate this equation over 0 to L, J is constant, and you just get that the current has to scale like delta T over L, and the temperature profile has to be linear. And that's just Fourier's law and the resulting temperature profile that you'd expect in one dimension. Now, that means that if you take, okay, first of all, normal transport is mediated by a diffusive mode or diffusive behavior. That means that if you take a system and you give it a kick, what you excite is a diffusive mode, and that will be responsible for normal transport. Now, then when is transport anomalous? Well, if you also add or if you consider momentum conservation, we know that momentum conservation is related to translation invariance, and it introduces a sound mode which goes ballistically. So for example, you can think of modes of a harmonic chain, right? If you just try to drive a current through a harmonic chain, then you just excite a mode and it carries the energy all the way through. It doesn't interact with other modes, and there is no diffusion. And so nothing depends on L, the length of the system. So the current will just be proportional to the temperature difference. And these are the kind of modes that you have by just having momentum conservation. Now, super diffusion arises when, so what I'm saying is I'm simplifying significantly the picture. This is related to this nonlinear fluctuation, nonlinear fluctuating hydrodynamics by Herbert Spohn. Super diffusion in this picture arises from nonlinear coupling between the diffusive mode and the sound mode. So it looks something like this. So if we are looking at, say, an energy-energy correlator like before, it would have this diffusive sort of behavior, but it will also have these ballistic peaks that fly away. And this interaction between the heat mode and the sound mode here is what generates. Heuristically, you can think that the sound modes pull on the tails of the diffusive mode and make it super diffusive. And this is what it looks like after long times. So now that we kind of have some sort of understanding of how normal transport shows up and what you need to get anomalous transport, we can talk about the signatures of anomalous transport. And I'm saying that these are asymptotic signatures. So they are not, you can't say that these signatures are only valid in the asymptotic limit. And as we now see what this means. So in equilibrium, you see super diffusive fluctuations. So systems that exhibit anomalous transport, if you study them in equilibrium, you see these super diffusive fluctuations that we talked about before, and this happens when time goes to infinity. And now, in non-equilibrium settings, what you have is an anomalous energy current, a current that doesn't go like delta T over L, but rather it goes like delta T over L to some power. This power goes between 0 and 1. So it's somewhere between ballistic, which is L to the power 0, and diffusive, which is L to the power 1. And you kind of see the special cases here. And in addition, this always comes together with a singular temperature profile. And these are all in non-equilibrium. I'm talking about stationary quantity. So there is no time here. We already waited an infinite amount of time, and the system has reached the stationary state. So what do I mean by a singular temperature profile? It means that asymptotically, the temperature gradient looks like this, where eta is some positive power. And it shows you that at x equals 0 and at x equals L, the gradient has a divergence. What this manifests as, in the temperature profile, it manifests as these sort of singularities at the edges of the temperature profile. Whereas in the bulk, you definitely see something that looks like a linear profile, right? Like what you'd expect from normal diffusion. But nevertheless, these features don't go away, even if you take delta T to be smaller and smaller. So they are not a result of nonlinearity due to strong driving. That's not where they come from. They are intrinsic to anomalously transporting systems. And if you look at one of the many reviews on anomalous transport, then you will see these are the signatures that people observe. Now, what about beyond the asymptotic limit, right? So I showed you the asymptotic signature. So to answer that, I'll note that in the asymptotic limit, the Lévy walk models these signatures very well. It also has the same signatures of anomalous transport, the Lévy walk model. And the question that we would like to ask is, do Lévy walks also describe anomalous transport beyond the asymptotic? So to answer that, I want to tell you about a recent study of a 1D gas model, which is of the same universality class as the previous system I showed you, with beta equal to 5/√3. And we derived this linear response relation between that it relates the energy correlation function in equilibrium to the stationary non-equilibrium behavior, the current and the temperature profile in the linear response regime. So delta T over T is much less than 1. Now, using the framework of nonlinear fluctuating hydrodynamics, we've shown that this correlator is, again, asymptotically, it's super diffusive, which is nice. But then we found that there is a correction which is diffusive. So going back in our minds to Lévy walks, then we know, wait, just a second, that's exactly what we'd expect, right? For beta larger than 3/2, we'd expect a diffusive correction. And this manifests in the stationary current that you see outside equilibrium. So the asymptotic behavior scales like 1/L to the power 2/3, which is on par with what you'd expect by everything we've discussed so far. And you'd also find a linear correction. So how do, this is a recent work again, and we see here the current, okay? The simulated current is denoted by these black diamonds, you see here. And now you see that the normal contribution, we were able to compute separately both the anomalous contribution and the normal contribution for this particular model. We were able to compute them. And these are what you would expect. These are the theoretical predictions. And you see that you need to take both of them. When you add them up, which is this green curve, you see it falls exactly on top of the simulated results. So you see that you really, really need both contributions to describe the current at finite lengths. And you see that the lengths here are, I mean, they're big. There's a finite density of particles here. So this is, order of this number of particles, which is a very big simulation that took a long time to run on our cluster. And so even at very large system sizes, you still need to take into account this correction. And it's very clear why. In order to distinguish between this and this, the ratio is L to the power 1/3. So you need the system size to be larger than 10 to the power 3 in order to tell them apart. You need to be much larger than that in order to say, I only have the asymptotic behavior. This kind of shows you that these corrections are really important in any real scenario, any real application you'd want to use. So does this imply that Lévy walks model anomalous transport beyond the asymptotic limit? Well, it's evidence that suggests that it does, but let's see. I mean, we've so far only discussed Lévy walks in equilibrium. Let's see if they can recreate this normal correction outside equilibrium. And this is another paper, another work in which I studied Lévy walks on a finite interval of length L under non-equilibrium settings, and I was interested in the corrections. So motivated by anomalous transport with beta equals 5/3, I studied this model, and again, under non-equilibrium settings, beyond asymptotic means finite L, L not equals infinity. Okay. Now, at this point, I owe to myself to note that there are only 2 more slides until the punch. So I'm sorry if I've exhausted you so far, but please bear with me for 2 more slides, and I promise it will be worth it. Now, I studied this behavior for beta larger than 3/2. There are complications at beta equal to 3/2 or less. But I was interested in this universality class of beta equals 5/3, which is in this regime. Just studying the equation for Lévy walks, the one that I showed you in the beginning that describes the model, you can write down a stationary equation that relates the energy currents this case, the current of Lévy walkers in the system to the density profile of Lévy walkers. And I should say, the system is again just a Lévy walk. So these guys are just the Lévy walkers from before, only now they are on a finite interval of size L, and they're connected to reservoirs of constant density of Lévy walkers. So here, in this reservoir, there's one constant density of Lévy walkers, and in the other, another constant density of Lévy walkers. And we'll be interested in the current of Lévy walkers between these two reservoirs and the density profile. So you can derive an equation, an integral equation again, that relates the current to the density profile. This sort of integral equation is called a weakly singular Fredholm integral equation of the second kind, which is a mouthful, but it just goes to tell you the weakly singular part comes from the fact that the integration kernel here is singular. So you see that when y is equal to x, this explodes, but this singularity is weak. So in the principal value sense, it's integrable singularity. And it's of the second kind because in addition to this integral, you also have this linear term in p prime of x. Okay. Now, you can derive this equation, which is great, and it really relates the current and the density profile. So in principle, you can get the current, right? And importantly, these have different coefficients, different powers in L, these two terms, where L is again the system size. Now the problem here is that it's relatively easy to derive this equation, but there is no general solution to it. So you can't solve it. You can write it down, but you can't solve it. However, there is a known solution if you take L to infinity and consider the asymptotic form of this equation. So you just get rid of this term. And even this is quite remarkable that you're able to solve this complicated integral equation, and it's very complicated. See, I mean, the current is constant. So what you have to do is you have to have the density profile exactly compensate for, for any point in space in order to keep this current independent of space. It's highly non-trivial equation, and its solution is non-trivial either. But the asymptotic behavior is known, and it was found. And remarkably, it has exactly the same form that we talked about before. So it has this singular density profile. Beta is between 1 and 2, so this is actually in the denominator. And the current is anomalous. It has this sort of scaling with L. Now, again, our question is, can Lévy walks recreate the normal correction that we saw in the gas model, right? That's what we want to answer. And the answer is yes. And I'll show you how. It's very simple in principle. If you take a perturbative approach to this equation, then, by which I mean you replace the density gradient by an expansion, a power series that decays with L. And you also replace the current, the stationary current, by a power series that also decays with L. Then, first of all, this series converges because when L goes to infinity, all of the corrections decay faster and faster. And what you get is replacing this, unsoluble integral equation by a hierarchy of soluble equations of the first kind, which is the only ones we know how to solve in general. So you get an order by order perturbative expansion of this equation that allows you to compute these guys. So at the leading order, you just find the asymptotic equation, which is great. That's exactly what you'd expect. And you can solve that, and you plug the solution into the next order, and you get another equation that you can solve because this is not a variable. This is something that you already know. And you can solve them order by order this way, iteratively, and you can get the corrections as far as you'd like to go. And so this figure kind of shows this. So again, I consider beta 5/3 because that's the motivation of this study. And here you see the horizontal axis is L to the power -1, which means that larger systems are along this direction to the left. And what you see in dots here are just the numerical solution of the model. You can numerically solve the equations for the Lévy walk. And you see here, in the green diamonds are just asymptotic current that you get. And the orange is the asymptotic plus the correction, the diffusive correction. And indeed, you see that it does a much, much better job of describing the real results than just asymptotics. The inset shows this is the asymptotic plus the leading correction over the numerical value versus just the asymptotic over the numerical value. And you see this is much closer to 1 as n goes to infinity. Then it does a much better job than just looking at the asymptotic behavior. And you also get a nice prediction. I mean, you can also, with this, solve the corrections to the density profile. And these corrections are also singular, just like the asymptotic form. And you see that, okay, here we wrote down this expansion. And if you just move P0 prime to the other side and you multiply by this constant, by L to the power 2 minus beta, you see this is what I compute analytically from that expansion, and you see that as the system size gets larger and larger, then you get a better and better approximation of that. So this shows that it's valid. So the normal correction supports the claim that Lévy walks describe super diffusion beyond the asymptotic limit. Now, I want to talk about what's left. I mean, there's a lot left, but a few directions to consider. So the first thing and the most important thing, as far as I'm concerned, is that there is more additional experimental proof that's required to validate that Lévy walks do model superdiffusion beyond the asymptotic limit, in equilibrium, outside equilibrium, in any setting. Another interesting thing to wonder about is why is the approach of superdiffusion towards the asymptotic form universal? Why should it be universal? And if it's universal, then why is the transition at beta equals 3/2? I mean, it's not intuitively clear, right? But this is a work in progress that I hope to be able to share within a few weeks that clarifies this question. And so finally, we see that in equilibrium, we saw that this onset of superdiffusion shows up in the mean square displacement, which is an observable that we are interested in. Outside equilibrium, we saw that it appears in the current and in the density profile. Are there other additional observables that are interesting that would be affected by such correction? Again, this is still open. So to conclude, the onset of superdiffusion in Lévy walks transitions between two types of behaviors, diffusion above 3/2 and superdiffusion below 3/2. This transition is universal, and it only depends on the heavy tails of the walk time distribution. There are evidence that suggests that Lévy walks might model superdiffusion beyond the asymptotic limit. These evidence are in 1D anomalous transport. But again, this is pending additional studies. And I think it's an exciting opportunity to look experimentally at these systems because now you have more control over them. So knowing these corrections, I think would make it much, much easier. I mean, I've seen lots of literature where people try to fit all sorts of data to Lévy works, and it's always very, very messy. Not always because the data is noisy. It's just because they find all these weird exponents and they go up to the 4th and 5th digit, and you don't know what you're looking for. It's like looking for a needle in a haystack and not knowing what the needle looks like. So I think this might be a good window into this thing. And on a personal note, I think that there is a Lévy walk hiding in at least many super diffusive phenomena beyond the asymptotic behavior. Now, if this is true, then this transition should be observable in experiments, and it should make super diffusion easier to observe. And I would be thrilled to collaborate with any group that's interested in pursuing this effort. And I thank you for your attention.
Okay, thank you. It was really nice. Questions?
Yes, I have a question.
Please go ahead.
Hi, Asaf. My name is Ron. I'm currently a postdoc at your department, so it's nice to meet you. I wanted to ask, are you limited to betas larger than 1, or do you go even lower than that?
So beyond, bless you, beyond 1 or below 1, the behavior is no longer super diffusive. It becomes super ballistic. And I mean, that's an important subtlety, because I mean, maybe I can go back to it. It'd be easier to see. This would imply that the first moment diverges. Now, I personally don't know of any system where would this be here. So I don't know any system in which there is no mean. It would mean that like every step you'd make will just explode immediately. So I don't know. I don't know any physical system that does this.
Okay, so I'm an experimentalist, and I'm doing stuff in turbulent flows.
Okay.
There's a well-known case for pair dispersion in which the mean square displacement goes as time to the 3rd power, meaning that data is 2/3 in your case.
Wait. If the mean square goes to the 3rd power, then it's sub-diffusive, not super. I mean, it's the other direction, right?
No. It's very quick. It's super diffusive. It's above the ballistic.
So it's super.
You call it a super. Yeah, you call it a super ballistic. Yeah.
This is the Richardson.
Yeah, exactly. Yeah. In any case, I have a lot of experimental data on particle tracking in turbulent flows, and I think we have a lot to talk about. So maybe we should.
Great, I'd be more than happy to. So, I mean, first of all, I'll be available later on. If anyone would like to talk, then please send me an email. I'd be more than happy to. And yeah, sure, let's discuss it, of course.
Great, let's talk.
I have a question.
Sure.
In the anomalous transport example, I mean, isn't there any role for the density field? Because it will determine the rate of collision locally.
Well, okay, again, there are no collisions here, right? The Lévy walk, I'm sorry, maybe I didn't clarify this, but the Lévy walk is a non-interacting model. So these guys, they don't know about each other. The transport here happens because you have basically a larger density here and a smaller density here. And you just have more particles going from one side to the other. That accounts for the curve. And diffusion is actually built into each particle. It doesn't have to talk to anyone else.
I was talking about the energy transport, these anomalous fluctuations in the energy.
Oh, sorry, not the Lévy walk model, but rather so maybe this gas model.
Yeah.
Okay, sure. Then sorry, could you please repeat the question?
So we were talking about a conservation of energy and then conservation of momentum in order to have these sound modes.
Yes.
So there is also a density field, and it's important, I think, because you get locally different collision rates.
That's true. So first of all, if you consider the linear response regime, then you're always interested in equilibrium correlation functions. So what you're actually studying is perturbations around a flat profile, right? Now, it is true that, I mean, we know that the equation of state of such systems, like a gas system, kind of relates, right? It relates the density field to the temperature field in a linear way.
Okay, so I see.
Yeah. I hope this answers.
Yeah. So it's coupled through the velocity of sound, which you take as constant.
The sound velocity, yes, it's constant, yes.
I have a question. So in many of the experimental systems, I should say in all my experimental systems, there's always dissipation.
Okay.
Always. There's no energy conservation. I don't know even how to really measure energy conservation, even in equilibrium when you're in an overdamped colloidal suspension, for example. But even if you have, I mean, so the conservation laws are not held in these experimental systems. So what can we do about it?
So that's not a requirement. It's just an example. So I mean, you see that. Sorry, I'm going quickly back to the slideshow. Bacteria don't conserve energy either, right?
Right.
So I mean, these are just what's nice about this Lévy walk business is that it's a model. It's just a toy model, and it models the phenomena. The settings, the physical settings, aren't that crucial. I mean, it works fairly. I mean, it works equally well, I would guess, studying fluctuations in 1D and anomalous transport, as well as any other system that has superdiffusion. If you believe that superdiffusion comes from some underlying Lévy walk thing, and I like this. So again, it's a belief thing, right? Because I mean, but I like this picture because it's physical and I can understand it. So we saw that in the generalized limit theorem, this sort of picture where you have correlated motion and the correlations just simply don't decay very fast is a very physical kind of model, right? I mean, you can imagine a huge array of systems that have these features. And you see that this is basically Lévy walks. Lévy walks is basically the generalized limit theorem with this interpretation.
Yeah, but it's only a different interpretation. Yael, for your question about dissipation, there is a very nice example of an experiment by Uzi Landman years ago, I just don't remember the year, where he looked at the motion of gold particles on a well-structured two-dimensional surface. And of course, there is dissipation there. And he can relate it, or even I think we related it, to a Hamiltonian system with an egg crate potential, which creates, numerically at least, beautiful Lévy walks. Now, the Lévy signature appears very, very in a pronounced way in the experiment of the motion of the particles that look as if they are Lévy, if there is a Lévy, I would say, fingerprint, but dissipation, of course, introduces some cutoff, but in an interesting way. So there are examples.
So my guess is, I think my guess is that if you take active systems where energy is constantly pumped in and dissipated, you might see Lévy walks and things like that.
I mean, as long as you have some, again, some motion that you can think of in these terms, then the details, I think, are, you know, there are many scenarios where this shows up. So I know that it does show up in turbulence, as I think Ron mentioned, it shows up in many different scenarios. So this is, again, a kind of a very...
I mean, I know that you can see Lévy walks in experiments. I was just somehow got the impression that for the model that you were using, you needed conservation laws.
So again, this was just this particular example. It's not necessarily a universal truth. I mean, again, there are, so you see, the results are for Lévy walks, and they are mutually exclusive of the example that I showed.
A very nice experiment, again, is the experiment by Sweeney, who looks at particles within two concentric rotating cylinders. He wanted to mimic some atmospheric motion, but this is a very, very clean experiment that shows very large leaps. You can look at it as correlated motion, but Lévy walks described it beautifully. He also has something else because he has also eddies. So he has another anomaly there, which is very long waiting times within the eddies. So this is a combined experiment of flights, or not flights, long walks, which look like flights, and also local spending time, which is also parallel. So there are experiments over time that one has just to recover them.
So wait, so these concentric cylinders are, there's a fluid in between them?
Fluid, yes, yes,
okay.
yes.
Okay, so there are particles that are suspended in this fluid and the concentric, okay.
Right.
I wasn't aware, okay.
And just a last comment. First of all, I would like to thank you in the name of Lévy walks. But the corrections here, I think, are better than what people used to do, is to introduce the deviation from asymptotics by having truncated Lévy walks, which is looking at the parallel
cutting off the tail.
And cut, exactly. And then it means only introducing a new parameter that helps fit the data. And this, what you presented, it looks to me a bit more physical.
I think so too. Thanks.
Okay, any more questions, comments? In this case, let's thank Asaf again. It was fantastic. And everyone who wants to do an experiment on Lévy walks, please contact Asaf.
Take care.
תודה רבה.
Thank you.
בכיף.
תודה.
תודה רבה.
בכיף. תודה לכם.
להתראות.
תודה.
להתראות, ביי ביי.
ביי.